Sometimes it is useful to determine whether two propositions are logically equivalent. For example, let's say in an application the user input should be a value between 0 and 10 inclusively. If the user enters an invalid value, then the user should be asked to re-enter a new value. We can write a while loop that asks the user to enter a value until a valid value has been entered. Thus, while the input is invalid, the user is asked to re-enter value. Hence the loop condition should be true if the input is invalid, and it should be false if the input is valid. The input is valid if the input value is greater than or equal to 0, and at the same time less than or equal to 10. Now we only need to negate this to get the loop condition, not, in parentheses, input greater than or equal to 0 and input less than or equal to 10. That is the first version of the while loop. Here's another version of a conditional expression. The input value is invalid if the value is less than 0 or if it is greater than 10. Thus the alternative while loop condition is input less than 0 or input greater than 10. So which version is correct? Don't they both make sense? We'll find out soon which version is correct by transforming propositions. When are there situations to transform propositions? We might want to simplify a proposition, or we want to show that a proposition is a tautology or contradiction, or we want to show that two propositions are logically equivalent. When transforming a proposition, we basically apply some rules called logic laws. Each logic law is nothing else than a well-known logical equivalence of two specific propositions. We'll step through several logic laws. There are two versions of De Morgan's law. The first one says that if we negate a conjunction, then this expression is equivalent to negating both operands of the conjunction and then replacing the conjunction by a disjunction. We get the second version of De Morgan's law if we swap the role of the and or operator. The implication law says that a proposition of the form P implies Q is logically equivalent to not P or Q. The double negation law says that we can drop a double negation. You know distributive laws from algebra. For example, if A, B, and C are numeric values, then we can use the distributive law to rewrite A times B plus C in parentheses as A times B plus A times C. The distributive law of logic works similarly. Here the conjunction plays the role of the multiplication and the disjunction plays the role of the addition. Interestingly, we can swap the role of the and or operator and the distributive law still holds. This is not the case with multiplication and addition. That is, the distributive law does not hold if we swap the role of the multiplication and addition operator. The commutative law holds for the conjunction and the disjunction. The identity law says that the truth value of P and true is equivalent to the truth value of P, and the truth value of P or false is also equivalent to P. However, P or true is a tautology, that is, it is equivalent to true according to the domination laws, and the proposition P and false is a contradiction, that is, it is always false no matter what P's truth value is. I'm sure you are familiar with the associative law for addition and for multiplication. The associative law holds for conjunction and for disjunction. The idempotent law says that P or P, as well as P and P, is logically equivalent to P. The absorption law says that the proposition P or P and Q is logically equivalent to P. Note that the truth value of Q is irrelevant to the value of P or P and Q. Analogously, the proposition P and P or Q is logically equivalent to P. The last logic law we consider is the negation law. The negation law says that P or not P is a tautology, and that P and not P is a contradiction. Generally, a proposition is transformed by replacing the proposition or a part of it by a logically equivalent part. The logic laws help us to figure out logically equivalent propositions. The goal of a transformation is to derive a proposition that is logically equivalent to the original proposition. Let's see two examples. You might have a formula that corresponds to one of the propositions in the logic laws. For example, the formula x or y implies x and z is a disjunction. The second operand of the disjunction is a conjunction. That corresponds exactly to one of the forms in the distributive law. Note that the expression here looks more complex than the propositions in the distributive law, because the logic variable q in the distributive law corresponds here to the compound proposition y implies x. Applying the distributive law results in the formula x or y implies x and x or z. In a different scenario, we might just replace a part of a proposition by a logically equivalent one. Consider the same formula as in the previous example. Note, it contains the implication y implies x. According to the implication law, this implication is equivalent to not y or x. Thus we can replace just the implication by not y or x, while all other parts of the original proposition remain the same. Now let's go through several steps of a sample transformation. We start out with the proposition P and not R implies Q and Q implies not R. Note that all logic laws we introduced, except for the implication law, use only the negation, conjunction and disjunction. It is often helpful to remove the implication operation, because then our chances are better that more logic laws can be applied. So in the first step we apply twice the implication law to replace both implications by disjunctions. Now we can use De Morgan's law to convert the subformula not P and not R. We negate P and not R, and the and is turned into an or. So the resulting proposition is not P or not R or Q and not Q or not R. Note that the last part of the proposition has not been changed. According to the double negation law, we can drop the double negation in front of the logic variable R. We can also drop the parentheses surrounding the first part, not P or not R, due to the associative law. That step is not straightforward. The associative law does not tell us directly that we can just drop parentheses, but instead it tells us that we can change the parentheses. However, changing the position of the parentheses means that we can evaluate a disjunction with more than two operands, and similarly conjunction, in any order. The outcome will always be the same. Therefore, we don't have to specify at all in which order to evaluate the disjunction or conjunction respectively, and we can completely drop the parentheses. I would like to go back to the two while loop versions that perform the input validation we considered earlier. We can represent the statement input is greater than or equal to 0 by the letter P. We represent the condition input less than or equal to 10 by the letter Q. Then the loop condition is not P and Q. If the input is not greater than or equal to 0, it is less than 0. Thus the condition input is less than 0 is represented by not P. Similarly, the condition input is greater than 10 is represented by not Q. Then the conditional expression of version B of the loop condition is not P or not Q. Now we can see that the two loop conditions are logically equivalent due to De Morgan's law.